It's often said that the theory of relativity proves to us that time and space are relative. Indeed, this appears to be an inevitable consequence of Einstein's famous speed of light postulate, which states that inertial observers must always measure the speed of light to be constant, no matter what their own speed is. Alas, there's a world of hidden meaning in the word measure, which, when scrutinized sufficiently, gives rise to a particular disconcerting loophole to the theory. And should we choose to exploit this loophole, it can allow us to do what's been considered unthinkable blasphemy for the past century: restore absolute space and time to modern physics. This is Dialect with The Loophole in Relativity.
The speed of light is constant, and it always shows the same value for all frames of reference.
One of the most fundamental physics facts is that the speed of light in a vacuum is constant for all observers.
The speed of light is measured to be exactly the same by everyone, no matter what.
Astonishment. Physicists discovered that this precise speed is absolute. Any object moving at 299,792,458 meters per second will have this exact speed in all reference frames. It is called the speed of light.
It's the inviolable law of modern physics. Each and every observer must measure the speed of light as constant relative to their own frame of reference. But what if this wasn't a law at all? What if, truthfully, it was just a narrative? Okay, come on, what do you mean, narrative? As all those videos clearly stated, that observers measure the speed of light to be constant in any inertial frame is a well-known, well-proven, well-demonstrated scientific fact. Well, yeah, except that it's not. You see, there's actually a bit of a hidden caveat to the speed of light postulate most people don't know about. And what it tells us is that it's not the speed of light which is measured to be constant for all observers, but rather the two-way speed of light which is measured to be constant. What's a two-way speed? Well, it's where you take something like a beam of light, fire it, reflect it off something, and when it returns to you, make a judgment about its average speed based on the round-trip distance traveled and the total trip duration. In contradistinction, a one-way speed would be firing a light beam in only one direction and measuring the time it takes to cross a given distance. Now comes an incredible fact. No one has ever measured the one-way speed of light before. All our measurements of the speed of light are two-way. Now, Veritasium already covered this topic in a very excellent video a few years back, which we'd highly recommend you watch. But the gist of it is that every empirical experiment which has ever been performed in order to measure the speed of light has always utilized a two-way measurement, because it's actually impossible to carry out any sort of one-way measurement. Thus, when we say things like that the speed of light is constant relative to all observers, this is actually unfactual, as it neglects the reality that there's an entire subset of one-way measurements we've never been able to make. Now, before you object and begin writing something in the comment section about how we must know the one-way speed of light to be constant because of this or that, please take a minute and scroll through the 100,000 plus comments on Veritasium's video, as you're likely to find your idea or objection already addressed there. Now, Veritasium does a relatively good job at going through different types of experiments you might try to set up and demonstrating why in particular they'd fail. But he only vaguely dances around the fundamental reason for why it is that we have never measured the one-way speed of light. Essentially, that reason is because we don't have anything to measure the speed of light relative to. To measure the one-way speed of light would require utilizing a signal much faster than that of light, which we obviously don't have access to. In the absence of a faster signal, measuring the one-way speed of light across a given distance requires first synchronizing two spatially separated clocks. But two clocks can only be synchronized by first passing information between them in the form of light signals. See where the problem lies? To measure any one-way speed, we must first adopt a synchronization convention. But this in turn requires making an assumption about how light travels from one clock to the next. Einstein understood this very clearly, because adopting a synchronization convention constitutes the first and foremost part of his famous 1905 paper. Here, he acknowledges that our empirical conception of the speed of light is in fact a two-way one. Then, to resolve this issue, he makes the most crucial assumption of his career. In referring to two clocks A and B, which are in the process of being synchronized, he writes, "We have not defined a common time for A and B, for the latter cannot be defined at all unless we establish, by definition, that the time required by light to travel from A to B equals the time it requires to travel from B to A." This assumption yields the resultant Einstein synchronization condition. Okay, halt the presses. So Einstein assumes that light must travel between two clocks in a completely symmetrical fashion, no matter what the speed of the observer is. And then he defines time for each and every observer through this assumption. Well, if the one-way behavior of light is symmetric, or more formally isotropic, for you, then for light to still have a constant speed everywhere means the one-way behavior of light must be asymmetric or anisotropic for observers in motion with respect to you. But because they also assume isotropic light behavior in their own frame, they'll synchronize their clocks differently than yours. Thus, plainly we can see that the relativity of time and space is a direct consequence of this assumption about the one-way behavior of light. But therein lies the problem, because this assumption is completely arbitrary. If the one-way speed of light is not empirically observable, this means it's equally probable that in synchronizing your clocks A and B, the light signal you sent out from clock A traveled at a slower than speed of light velocity towards clock B, then zipped real quick back towards clock A at a faster than speed of light velocity, or vice versa, such that the total average speed was that of the speed of light. If this happened to be the case, then the notion of length, time, and simultaneity you constructed in your frame using Einstein's assumption would in fact be a false one. Indeed, it didn't take long after 1905 before others picked up on this arbitrariness in Einstein's assumption. Most notable to do so was the philosopher Hans Reichenbach, who in his work The Philosophy of Space and Time described the notion of simultaneity as being regulated by a sort of uncertainty principle. "Simultaneity is not a matter of knowledge," he wrote, "but of a cognitive definition, since knowledge of simultaneity is impossible in principle." Reichenbach asks us to consider three times, T1, T2, and T3, corresponding to the respective times that a light signal is sent out from clock A, that it reaches clock B, and then returns again to clock A. Simultaneity can then be defined via the following relationship. T2 equals T1 plus epsilon times T3 minus T1, where epsilon represents the uncertainty in the one-way speed of light and can range from anywhere between 0 and 1. As Reichenbach points out, the Einstein convention chooses a value of 1/2 for epsilon. This means we assume the light beam in our frame spends half the total time traveling from clock A to clock B, and half the total time traveling back. If we instead choose a value of 2/3 for epsilon, this would mean we assume the light beam in our frame spends 2/3 the total trip time traveling from clock A to clock B, and 1/3 the total trip time traveling back. As Reichenbach clarifies, we are free to choose whichever value of epsilon between 0 and 1 that we like. Just like deciding where the origin of a coordinate system should be, it's a completely arbitrary choice. Einstein's convention, Reichenbach notes, does achieve greatest mathematical simplicity, as choosing a value like 2/3 for epsilon would lead to quite the headache mathematically for observers. But Reichenbach makes it clear the choice of 1/2 for epsilon is not an empirical necessity, but rather a mathematical stipulation. He then goes on to note that determining absolute simultaneity would require a faster-than-light signal. So unfortunately, observers are stuck with choosing some value of epsilon, whatever it may be. From this he implies that space and time must still ultimately be relative, even if it's not quite the mathematically simplified version of relativity Einstein presented. But here Reichenbach neglects one incredible, crucial point. He, along with Einstein, implicitly assumes all observers must choose the same value of epsilon. But nothing restricts different observers from choosing different values for epsilon. This is our loophole. Because different observers could always choose different values for epsilon, such that their notions of simultaneity wind up being the same. That is, given any collection of observers A, B, C, etc., whose velocities with respect to some given frame are v1, v2, v3, etc., we can always find a corresponding set of epsilon values, epsilon 1, epsilon 2, epsilon 3, etc., such that each and every observer constructs the same notion of simultaneity, and therefore the same notion of space and time. And thus at once we've done the impossible, restored Newton's notion of absolute space and time to relativity. This is easiest to grasp with a space-time diagram. First, take a given observer who considers themselves to be at rest and is synchronizing their clocks with light signals. As they move through time, their space-time diagram will look like this. If they adopt Einstein's epsilon 1/2 convention, they will draw their line of simultaneity directly down the middle like this. Next, consider an observer in motion relative to this first observer, who is also synchronizing their clocks using light signals. If this second observer also uses the 1/2 epsilon convention, then they will draw their line of simultaneity such that it will appear slanted relative to the first observer. Because these planes of simultaneity are slanted with respect to one another, time and space will then be said to be relative for the two observers. But now we can recognize that there's no real reason the second observer has to adopt the epsilon 1/2 convention. They could instead adopt a different value, such that their plane of simultaneity would align with the first observer's. Then, between these two observers, there will be total agreement on all notions of time and space. Physically, this amounts to choosing a particular master frame, and having all observers agree that the clock ticking in this frame represents true universal time. But of course, in special relativity, choosing such a privileged frame is disallowed, since the principle of relativity requires that the laws of physics take the same invariant form in every inertial frame of reference. But again, we can see the circularity here. The laws of physics are expressed via space and time, so for them to indeed take the same form in all inertial frames of reference requires all inertial observers to build their notions of simultaneity according to the exact same recipe. Meaning observers would all have to choose the exact same epsilon value. meaning it would have to be factually true that the one-way speed of light was the same for every inertial observer everywhere, in order for it to be factually true that the laws of physics have the same form in every inertial frame. But again, the one-way constancy of light is not a fact. We thus assume one-way light's behavior to be isotropic, thereby contriving space and time to be relative, in order to give the laws of physics the appearance of having the same form for all inertial observers, because that's the mathematically beautiful description we prefer. This, of course, is the very definition of a narrative. Indeed, it wasn't until 1976, over 70 years after Einstein published his theory, that anyone would appear to hit upon the idea of different observers assuming different values for the one-way speed of light. Such a method was finally considered by these physicists in a paper entitled A Test Theory of Special Relativity, Simultaneity and Clock Synchronization. The conclusion they drew? A theory maintaining the concept of absolute simultaneity can be obtained in this way, which is empirically equivalent to special relativity. Okay, let's pause to summarize everything so far. Firstly, we've learned that the central assumption from which special relativity stems, i.e., that the one-way behavior of light is isotropic in all inertial frames, is empirically unverifiable. Secondly, we realize this implies observers are free to assume whatever one-way behavior of light that they like in their own frames, a choice represented by Reichenbach's Epsilon Value. Thirdly, for multiple observers, we know we can always select a particular set of epsilon values such that everyone's notion of simultaneity exactly aligns. Lastly, we note this doesn't change the laws of physics, it just changes how we express them. Naturally then, we should be led to ask, what exactly do we stand to gain in adopting the notion of absolute simultaneity? We can answer this by considering the physical meaning of anisotropic light behavior. If we send out a light wave in every direction, since the two-way speed of light is still factually a constant, then if light moves more slowly in one direction, it must compensate by moving more quickly in the opposite direction. Thus, for any spherically shined ball of light, if the one-way speed of light were anisotropic in your frame, the center of the sphere of light would move steadily away from you, like this. Values of epsilon further and further away from 1/2 would correspond to the sphere moving away from you at a faster and faster rate. Thus, it would be as if the light sphere were expanding at a constant speed in some particular frame, and you were in motion relative to that frame. Now, if you've seen one of our recent videos, what time dilation actually is, the puzzle pieces should be seriously starting to fall into place for you right now. Things come together even more when we make note of our prior observation, that if you attempted to synchronize your clocks in a frame where you assume the one-way behavior of light to be isotropic, when in fact that behavior was anisotropic, the notion of space and time you constructed would be a false one, a sort of projective map. Indeed, by conjoining this so-dubbed epsilon choice interpretation with that of dynamical relativity, we will be able to do what was supposed to have been impossible. Give a fully physical, fully mechanistic description to the theory of relativity. Yes, that means that everything from time dilation to length contraction to the symmetry of these things between observers in motion, all of this can be exposed as the consequence of simple, physically causal phenomena. Stick around with our channel and you'll find out exactly how. Now, finally, a big thank you to our Patreon supporters for continuing to make all this possible. Knowing how many people out there are looking for real answers has kept us motivated, kept us going. So until soon, this has been Dialect. Thanks for watching.